Buenos días. Es un placer presentarles a esta investigadora senior, Severo Ochoa, que va a pasar con nosotros. Uy, qué raro habla esto, ¿no? Depende mucho de cómo te lo acercas al... Vale. Manuela va a estar con nosotros, bueno, la profesora Manuela Zoccali va a estar con nosotros hasta el 12 de febrero. Y, bueno, aprovechen de su estancia porque es alguien con el que es muy interesante posiblemente iniciar colaboraciones y trabajos. Manuela hizo su tesis en Padua, en la Universidad de Padua. Posteriormente hizo un postdoc en la ESO y otro el siguiente en la Universidad de Princeton, en combinación con la Universidad Católica de Chile. Esto era una colaboración con la Fundación Andes. Y posteriormente fue contratada por la Universidad Pontificia, es que es muy complicado. Pontificia Universidad Católica de Chile como profesor, cargo que ostenta desde el año 2004. En el 2008 pasó a profesor asociado, que sería algo más que lo equivalente aquí a profesor titular, creo. ¿Sería el rango más superior que hay en Chile o el intermedio? Vale, tres escalas, pues sería la escala intermedia. Bien, Manuela se dedica sobre todo al estudio de poblaciones estelares, sobre todo en el bulbo galáctico y en cúmulos de estrellas. Y bueno, entre cosas a destacar de su carrera, ¿no? Fue el premio de la Fundación Guggenheim, una fellowship de la Fundación Guggenheim que recibió en el año 2011, y recientemente el proyecto muy bien, digamos, altamente competitivo, más otorgado por una... Bueno, ella lo va a contar mejor esto, bueno. Pero vamos, que ha sido... Yo creo que quizás sería algo equivalente a lo que aquí sería el Severo Ochoa, a lo mejor, ¿no? Sí, porque, bueno, solo lo han recibido dos... Sí, pero dos proyectos en todo Chile, uno de oceanografía, otro de astrofísica, y se ha otorgado a un equipo de 12 investigadores únicamente. Ella lo va a contar mejor que yo. Muy bien.
Gracias. Yo no sé si esto funciona, pero si no me escuchan, me avisan y quizá grito. ¿Funciona? Bueno, solo para completar lo que decía Karma, este Millennium Institute of Astrophysics, in English, yes. The Millennium Institute of Astrophysics is not really an institution like the Pontificia Universidad Católica. It's more a funding project, but we just got this funding for 10 years. And so I want to mention that just because we will have many postdoc grants that we will announce. So if you are interested in coming to Chile for a visit or some kind of grant, just talk to me later. So in this talk, I will show my work and the relevant work of other people as well about the galactic bulge. And this is something I have been doing with the collaboration of, let me mention especially my young collaborator, Oscar Gonzalez, who is now a fellow at ISO Chile, Sergio Vázquez, PhD student at PUC, Roberto Saito, former postdoc at PUC, now faculty in Brazil, and Dante Minniti, who is the PI of the VV survey that I will mention in a short time. Just let me mention that when I will talk about galactic bulge, I mean to refer to the inner 3 kiloparsec of our galaxy. I don't mean a special stellar population, but just what's in there. And we will try to characterize what's in there. So the motivation of this work is to try and understand how did the Milky Way form and to generalize that, if we can, on how do galaxies form. And in the context of the Milky Way, it is particularly relevant to study the bulge because in addition of being old, as we will see, it is also massive. So here I list the masses of the disk, the bulge, and the halo. And you can see that the halo is certainly the oldest component, stellar component of the Milky Way, but it makes up just a tiny fraction of the galaxy. So if we understand how the halo formed, we have in place just a little bit of the Milky Way, 100th more or less. So if we understand how the bulge formed, we have already 1/5 of the galaxy, which is a significant step forward, I think. And in the more general context of galaxy formation, why study precisely the bulges? Until a few years ago, I liked to show this kind of slides, trying to argue that bulges and ellipticals, they have a common name. They are called spheroids, and they share several properties. For instance, they lie on the same fundamental plane. This is true, actually, for some bulges that people like to call classical bulges. However, there are other bulges that look different. They don't share the property of elliptical galaxy. They look more like fat bars. And so there is, in the literature, it is, people often refer to a dichotomy between classical bulges and pseudo-bulges. That will be this, would be bulges that derive from dynamical instability of the disk, as we will see. I personally don't like too much this dichotomy, so I will try to not talk about this anymore in my talk. And the reason is that I think the process that gave rise to the bulge is something intermediate. Just to anticipate the conclusion, our bulge is about 10 giga-year-old, so it must have formed at Z2, more or less, at redshift 2. If we look at redshift 2 on the equivalent of galaxies like the Milky Way, they are very clumpy and gas-rich. So if we want to understand processes like dynamical instability of the disk that give rise to bars and bulges, we have to include gas. And if we include gas, we see that these gas-rich clumps eventually merge into the center, so can form bulges. So actually, there are processes like this that for sure occur because we see it occurring 10 giga-years ago, and they are something in between the poor disk instability that in some simulation give rise to the bars and some kind of merging that can give rise to classical bulges. Okay, so why precisely the galactic bulge? Because it is the only bulge that we can study in great details. It is, in particular, the only bulge that we can resolve into individual stars down to the smaller star, down to 0.1 solar masses. And since it is so close, we can also get high-resolution spectra for the brightest star. Just to put this thing in context, the next bulge will be the Bulge of M31. And you can see that Tom Brown, with several orbits of HST, could reach the turnoff of M31 at 11 kiloparsec from the center. So I wouldn't really call that the bulge. It's more like the inner halo. At 4 kiloparsec from the center, even with many orbits of HST, you cannot resolve the turnoff. So we are stuck to our own bulge. If we want to study in detail the stellar population, maybe the star formation history of one bulge. Okay, so this is our own bulge. And it has all the advantages that I just mentioned, but it has also problems. And some of them are pretty evident in this picture. First of all, it's full of patchy extinction because there are molecular clouds and dust in the plane of the disk. And we have to look at the bulge through the disk. We don't have another choice. And so this bothers. Going in the infrared helps, but doesn't solve this problem. The other problem is crowding, as you can see, in some fields. But another problem that is less evident probably, but we're starting now to realize that we have to take that into account, is that this thing is huge in the sky. That line is 20 degrees. And since it is not very homogeneous, it's pretty complex, if we want to get the global picture, we need surveys, large area survey. Otherwise, we really cannot characterize the whole thing that is inside more or less a radius of 3 kiloparsec. And so, during my talk, I will try to address the question that I put up there using the bulge structure, so basically the shape and the kinematics, the age, and the chemical content, not necessarily in this order. A little bit like babies, when they get a new toy, they look at the shape, see how it moves, and then make a chemical analysis. We try to do that, to try to understand what is this thing. So the shape. We have known for a long time that the bulge is a bar, in fact. So it is really elongated. How did we know that? We knew that already in '94, because Stanek, looking at the Kobe data, so near-infrared data, realized that on the positive longitude, on this side, the bulge is brighter than on this side. You see that it's kind of boxy, but not quite, more trapezoid, or I just make up a word. But anyway, on this side is larger, brighter. And it's not brighter because maybe there are more stars. It's brighter because stars on these sides are brighter individually. And this has been verified, for instance, looking at red clump stars that are distance indicators. And on this side, if this is magnitude, so this is a luminosity function in which this peak is the peak of red clump stars. Red clump stars on this side are brighter than red clump stars on this other side, just because they are closer to us. So it's a bar with some position angle with respect to the sun galactic center direction. And there are several, at least 10 studied, who characterize the bar. It's clear that there is a bar. It's something very robust. More or less, the bar has that axis ratio written there and an inclination angle or position angle with respect to the sun galactic center direction of 25 degrees. This varies a little bit depending on different authors, but it's of that order. The age is a bit complicated for the reason that I mentioned before, that we can only look at the bulge through the disk. And so if we plot a color magnitude diagram of the bulge in any filters that we like, what we see is the main sequence of bulge stars, the red giant branch of the bulge with the red clump that we were looking at before. And on top of the turn-off and the main sequence, we have the disk main sequence, which is a vertical diagonal sequence, because those are disk main sequence stars at different distance along the line of sight at different reddening. So that's why it's vertical and a little bit diagonal. And a similar sequence, although in this plot is saturated and not well populated, is the disk red clump. But the problem is here. To date bulge stars, we want to look at the turn-off. But the turn-off is not clean. It's heavily contaminated by disk main sequence stars. So we have to think about some way to get rid of those. People did this, being creative, but only for a few pencil beams in the direction of the bulge. So our knowledge of the age is really, in a sense, deficient. First, because we don't have a lot of precision, as you will see. And second, because we measure ages only in a few very narrow line of sight. So with my collaborators, we did this in 2003. And we could decontaminate the bulge color magnitude diagram from the disk stars using a disk control field. So statistically, we subtract stars, as we saw in the control field, from the bulge color magnitude diagram. This is quite rough as a method. It only works, first, if the stellar population of the control field is the same as the one contaminating the bulge, which is not strictly true because the disk is very clumpy. There are spiral arms and stuff. And second, you need also that the distance distribution and reddening distribution on the two line of sights are the same. And that's another mess. But as a first approximation, it works. This is the color magnitude diagram we obtained from the bulge. And as you see, all these stars that, let's say, could be either disk main sequence stars or bulge young stars disappeared. leading us to think that they were, in fact, disk main sequence stars and not young stars in the bulge. Another way of doing this, way much better, is what we did together with Clarkson et al., which is to decontaminate the bulge color magnitude diagram using proper motion. So we did a kinematics decontamination. Using 2 epochs of HST data, we could get proper motion of all the stars in there. And since the distribution of proper motion is different, although overlapping, otherwise it wouldn't be fun, we could get a bona fide color magnitude diagram of only bulge stars. As you can see, you don't need to read all this. I guess you cannot read it. But you can see that here, there are only a few % of stars left. And actually, 2 years ago, we also got spectra for most of them. And they show radial velocity variation, indicating that they are binary stars. So probably they are blue straggler stars. They also show luminosity variations, as expected for blue stragglers. So we have reason to believe that most of those are blue stragglers, and if there are some intermediate age bulge stars, they should be really a tiny %, like below 5%. And so this is a field at coordinate 0, -6, a little bit farther away than Bade's window. This is an inner, a more central field. There is another study that we did together with Elena Valenti et al. In 2 fields on the side of the bar, because people who do dynamical simulation of bar formation say that if there are intermediate age stars in the bar, they are expected to be at the edges of the bar. So we tried to look there. Again, we did the decontamination with a control field, and we clean up that part. So again, we don't have evidence leading us to think that there might be intermediate age or young stars in the bulge. Similar thing in this other side. So here there are several isochrones, but basically the point here is that we can exclude the presence of stars younger than 5 gigayears. This number is a bit important for what I will tell you later. And we did this also in another field in which the reddening, the differential reddening is pretty heavy, so we don't have a good pressure. These are Padova isochrone, and we also use the Teramo isochrones, and they give pretty similar results. Padova 2000. So basically, all this is to say that the age of the bulge from the color magnitude diagram is of the order of 10 gigayears, but we have an error bar of plus or minus 2 gigayear, more or less, because of the problem of disk decontamination. However, other people measure the age of a sample of bulge stars with a completely different approach. This is the group led by Bensby et al. What they are doing, they have an ongoing program for many years. They are getting high-resolution spectra of dwarfs in the bulge, so stars in the main sequence actually close to the turn-off, at very high resolution when they are micro-lensed by some lens in front. So they are magnified by several 100%, such that one can get a high-resolution spectrum. From the spectrum, you can get gravity and temperature. So they can construct this kind of plot and put the isochrone on top of that to assign an age to each individual star. By doing this, they can construct this plot with age and metallicity. For a sample of stars, they now have 50-something, 58, I think, stars in total. And they found kind of an age-metallicity relation. They find that at all ages, stars have all metallicities, or another way to say is that, a better way to say actually, is that for metal-poor stars, you can only see all the stars in the bulge. But if you go in the metal-rich regime, the age spread is big. Another way of saying it is that 30% of these stars, that are main sequence stars, have ages younger than 7 gigayear. And some of them are as young as 1.5 gigayears. which is something that really can be excluded from all the color magnitude diagrams that we could get. Because although the turn-off is pretty spread and we don't have a high precision, the presence of a significant fraction of stars with ages younger than 5 really can be excluded. So, 2 points here. One, we don't understand why they measure that. Or what you measure with this method is not confirmed from the color magnitude diagram. However, if we believe this, there is some indication that maybe there are 2 components in the bulge. So one metal-poor component that is only old, and another metal-rich component that has a large spread in age, if you believe that. But needs to be confirmed, I think. They are all over the bulge, and yes. So in this paper, they have a series of papers because they have been increasing the sample over the years. In this last paper, there is a discussion about possible biases, and they mentioned that they do have a bias in favor of young stars because the condition for them to get a high-resolution spectra is that the stars becomes brighter than 15 magnitude. In order to become brighter than 15, if the star is young, meaning that it's already brighter, then the star needs a smaller magnification. So they do have a bias in favor of young stars, but the young stars need to be there. Maybe not the 30%, maybe 20 or 15, but still we don't see any, virtually any, in the color magnitude diagram. And so they discuss that, and they think that this bias is not sufficient to reconcile the 2 results. Okay, so I want to mention that this is a possible indication of a multi-component or 2-component bulge. We'll see that we have several others, although they don't go in the direction of the presence of young stars. Let's move for a while to the chemical abundance in the galactic bulge. The first pioneer work on this, using high-resolution spectra, has been done by McWilliam and Rich, very famous work in '94. What they did is to go and observe 11 stars at high resolution, or high resolution 17,000, and they used these 11 stars to calibrate metallicity measurements in low-resolution spectra of 88 stars. So in the end, in this histogram, in the black one, in the gray shaded histogram, there are 88 stars, but only 11 of those have been observed at high resolution. So what they found is that the bulges are rather widespread in metallicity, with a peak around solar and a long metal-poor tail. Surprisingly, possibly, 12 years after, the method was pretty similar. The same people, now led by John Fulbright postdocs, with Mike Rich and Andy McWilliam, they observed now 27 stars to use as calibrator at a much higher resolution, and then they used that to calibrate a sample of 217 low-resolution spectra. They got this metallicity distribution that is fully compatible with this other one, although, of course, more detailed. So all that pointed to a very efficient star formation. But it was only with the advent of high-resolution multi-fiber spectrograph that you could really make a conceptual step forward, so that you could be, in the sense that you could obtain an histogram of some 100 stars, all with high-resolution spectra. And the first study in this sense was done by us in 2008. We had 3 fields marked here in green. Along the minor axis of the bulge, we got this 3 metallicity distribution. And then later on, Christian Johnson and collaborator got another field here in the middle, and a few other fields on the side. And what we all find is the presence of a gradient along the minor axis, in the sense that the innermost field, which is Bade's window, by the way, here, a low extinction window, is the most metal-rich one, and then when you move outwards, the mean metallicity starts decreasing. There is a little bit of a wiggle, because there is also discontamination in these stars. These stars are red clump stars, but there is some discontamination there. Depending on how you quantify that, you get a different, slightly different value of the gradients, but the presence of the gradient, I think, is out of discussion. It's pretty clear that it's there. However, Ricci, Orilla, and Valenti, in two subsequent papers, 2007, 2011, measured metallicity for a sample of stars in 4 fields, really in the inner bulge, between Bade's window -4 and 0, -1. And what they found is the absence of a gradient. As you see, the histograms are all centered in the same place. So, it might be, perhaps, that they have low statistic, but because they have only 15 stars in each of these fields, but I don't think so, personally. It might be that there is no gradients in the inner bulge, and the metallicity gradient starts in the outer part. So this is another indication that there might be maybe 2 components in the bulge. By the way, why the presence of a metallicity gradient is very important? Because it is what would be predicted if the bulge would form from a dissipational collapse. Instead, if you form a bulge from dynamical instability, some dynamical effect that creates a bar and then thickens the bar, you don't have reason to expect a gradient because the dynamics should be blind to the metal content of the star. So you really don't expect a gradient. That's why we are so hardly trying to understand if there is a gradient or not. No, it's just the scale is much expanded. If you see here, we get to -1.5, and here it is -0.6. So they are showing only this part. It's a zoom, but anyway, the peak is at 0.2, and here the peak is 0.2 is here, so it's more or less like this. It's lower maybe than Bade's window. No, this is 0. It's more or less. The scale is really not the same, sorry. So, other indications that maybe in the bulge there are 2 components. One comes from a study made by Hill et al. In 2011. I'm a co-I of that. We analyzed the metallicity distribution of a sample of 400 stars, so it's a statistically significant sample in Bade's window, and we argue that that distribution can be bimodal. I am a co-author of that paper, and I had a hard time to believe that that thing is bimodal with 2 Gaussians like that. But eventually, I got convinced that maybe there is some indication. And the reason, which I think is instructive, is that when you want to understand what is the real distribution that you are trying to measure with this data, you have to take into account the fact that data have errors, of course. So what errors do is to spread up what you observe. So if we want to try to analyze what is the real distribution, we have to try to deconvolve from observational error. In order to make a deconvolution, you need to smooth the data, which is the gray shaded is the error bar, smooth the distribution, and then deconvolve from observational error. And the deconvolved distribution really is bimodal. I'm not sure I myself believe that this in particular is the position of the 2 peaks and that there are 2 peaks. I just think that it's important to keep in mind that what we observe is convolved from observational error, and we have to get rid of that to analyze, to study the underlying distribution. However, a more robust argument is that if we do the kinematics of all the stars in there, which is what we did in the paper led by Karim Babuzio et al. In 2010, we see that the kinematics of metal pool stars, so this is metallicity, and this is vertex deviation, that is an instrument that dynamists use to try and quantify how, in a sense, how elongated is the velocity distribution of the stars. we see that metal-poor stars have a vertex deviation close to 0, while metal-rich stars have a vertex deviation negative and significant. What this means is that metal-rich stars have orbits distributed in an elongated ellipsoid, velocity ellipsoid, while metal-poor stars have more a spheroidal distribution. This goes in the direction that perhaps the metal-rich stars are arranged in a bar, so they have elongated orbits, and they have no metallicity gradients, because the bar is something that derives from dynamical instabilities, dynamical processes, while there is a metal-poor spheroid that is more symmetric, and maybe it is this spheroid that has the metallicity gradients. Maybe, maybe, maybe. I said maybe enough times, I hope. This is something stronger, I think, which is a result we obtained really a few months ago. This is, well, what we did is to take the special distribution of RR Lyrae stars that we obtained from the VVV survey. I will talk about the VVV in a second. Just here we take the special distribution of RR Lyrae stars in the bulge. For RR Lyraes, since they are robust distance indicator, you can get the distance of each of them. So the 3D distribution is pretty robust. And what I show here are horizontal cuts, as shown there, at different latitudes. And this is the density of RR Lyraes. So the sun is somewhere there. And as you see, there is no bar. It's a round thing. RR Lyraes trace the old metal-poor population in the bulge. Instead, red clump stars that we were analyzing before trace the metal-rich distribution, maybe even slightly younger. So metal-rich stars are arranged in the shape of a bar, while RR Lyraes are arranged in the shape of a spheroid. And we need to understand why. So with all these puzzles in mind, we are now entering the era of surveys, because I hope I convinced you that the bulge is not homogeneous. You cannot study Ball's window and say this is representative of the whole bulge, because there are gradients here and no gradients there. Different stars of different metallicity trace different shapes, so you really need a wide area survey. A first kinematical survey of stars in the Milky Way is the BRAVA survey, led by Mike Rich and later on Andrea Kunder. They obtained radial velocities for M giants, so really the brightest one, in several fields in different latitude strips in the bulge. What they found is that stars have cylindrical rotation. This means that the rotation of the bulge doesn't change when you go lower in latitude. So in a sense, the bulge is rotating as a solid body, more or less, cylindrically, which is something expected if there is only a bar in there. A spheroid is expected to have a significant variation of the rotation with latitude. So what they say is that we are in a bulgeless galaxy, in the sense that there is only the bar. This is the Howard paper, arguing about no need for a bulge in the Milky Way. Another survey is the Argos survey, led by Ken Freeman and Melissa Ness. They obtained spectra for, in total, 20,000 stars, 14,000 of which are inside what I'm calling the bulge in this talk. They have spectra in the calcium triplet region, but they are measuring iron in that region at 11,000 resolution. And these are all the fields they have. You cannot read, but this is -5. The inner they get is -5 in latitude, and they go to -10. And they cover a pretty wide range in longitude, from -20 to +20. So if they sum up all the spectra they have at each latitude, they obtain these three histograms at latitude -5, -7.5, -10. And they confirm the gradient along the minor axis pretty clearly. They go much further than this, of course, because they have a huge sample of stars compared to previous study. And what they do is to try to characterize the change of shape of the metallicity distribution by fitting it with 5 Gaussians, which is, in my opinion, a bit too much for the statistic you have, but you don't have to believe really the position of the Gaussian precisely. It's a way of describing in words or in numbers the changing of shape of this distribution. So they tentatively associate the 5 Gaussian to 5 different populations in the galaxy. The metal-rich Boxy peanut bulge, that is the A component, this one, that is pretty strong in the inner bulge. In the middle is significantly lower and almost disappears in the outer bulge. The vertically thicker Boxy peanut bulge, the B component, which is almost the same all over the place. And then a metal poor component that is relatively smaller in the center and stronger outside. And then the most metal poor stars are contamination from halo, most likely. Then there is the Gaia ISO survey that possibly several of you are co-I of. They have a huge amount of nights with flames, so they will soon shed light significantly on the chemical abundance in the bulge, but they don't have published papers so far for bulge. And then there is Apogee, which is also a near-infrared spectroscopic survey of a huge number of stars all over the galaxy. They are, at the moment, conducting the survey from the Apache Point Observatory, where they barely see the bulge, but they are soon coming to the south, so soon they will sample the bulge very extensively. And so waiting for that, for those two surveys, I will talk a little bit about the VVV that I mentioned rapidly before, which is the vista variable in the Via Láctea. It is not a spectroscopic survey. It is a photometric but multi-epoch survey. It's an ISO-public survey, so data are public right away, and catalogs are public every year, are becoming public every year. The survey is led by Dante Minniti at PUC and Phil Lucas in UK. The survey targets a square in the bulge, actually a rectangle, from -10 to +10 in latitude, in longitude, and from -10 to +5 in latitude, and also as a strip in the disk. We observe through 5 filters in the near infrared, and we repeat about 100 times the observation in the cave band. The main goal of the target of the survey is to sample variable stars in the bulge, and in particular, the times are optimized for irregularities. So we want to trace the old metal poor population. At the moment, we have completed all the area in the 5 filters, so we have the 5-band map of the whole bulge, and we are more or less halfway through all the epochs in K. So we are starting to detect variables and classify them. At the moment, we have released the data release 2, which has the multi-epoch, the 5-band catalog, and you can get the catalog at this link if you want. So this is the map of the whole bulge area of the VVV, and it's associated with the catalog that, as I said, you can download, and it's huge and it's beautiful. And just to convince you quickly that it's beautiful, let us zoom in. In. It is beautiful, it is. So, what can we do with this beautiful data? For instance, we can construct a color magnitude diagram. For the whole area, we published a color magnitude diagram with 84 million stars. And now with the data release 2, we have about 150 million stars. And then try to convince Karma to simulate that, which is why I'm here for. Of course, this color magnitude diagram is not really beautiful because it is just raw. This is the reddening vector, and as you can see, the red clump is very much spread along the reddening vector, so it needs a lot of things before going and talk to karma. One thing that it needs is that you model extinction, so that then you can try and remove it. And this is a high-resolution extinction map from the VV. The spatial resolution is 2 arc minutes in the inner part and 6 arc minutes in the outer part. And so you see that now we have a reddening map really very fine. You can get the reddening for any given position at this page. And you can also upload a catalog and so get the reddening at several positions if you need to. By using that map to correct the color magnitude diagram, you can then obtain a color magnitude diagram corrected by reddening and model the upper part of the RGB, not model, but derive the mean metallicity in each region from the slope of the red giant branch. And so in this way, you can obtain a photometric metallicity map of the wool bulge, which is that thing. This one has been published last year. It doesn't have the central part because then crowding and differential reddening was too big. This map is also beautiful. Why? Because as I said before, since the bulge is huge in the sky, we have trouble getting the global picture. And this helps us a lot in getting the global picture. It is the thing that you would compare with an external galaxy. So this is just the global view of our bulge as you would see if it was an external bulge. And there is one thing that is also beautiful in this map, is that I can see, and I hope you can see as well, 4 lobes here. Well, you certainly can see that here the metallicity is lower than here and here, and also here is lower than here and here. And you can also see, I think, that here is more metal poor than here. So it's not a spheroid, a symmetric spheroid. What are these 4 lobes? So these 4 lobes are beautiful because they are tracing the Boxy peanut bulge. What is the Boxy peanut bulge? I said before that the bulge is a bar, but in fact, this is only the inner bulge that is a bar. If you go in the outer bulge, you see an X shape or a peanut shape, very pronounced. Let's see that. We found this thing together with Andy McWilliam and then mapped this thing together with Roberto Saito in 2011 from 2 mass. So this is my own attempt at drawing what I see with Keynote. But we see an X tilted with respect to us, so that the 2 arms of the X that are on this side, darker green, are in front and are partially hiding the other 2 lobes that are in the back. It is very fortunate in a sense that this is tilted, because the way that we discovered this is that if you observe along the minor axis, you see 2 red clumps, because you are crossing first this overdensity and then the other in the back. And if you map this, so you map the distribution of red clump stars, use it as distance indicator, which is what we did together with Roberto Saito, you can construct, for instance, horizontal sections, horizontal meaning parallel to the galactic plane, of the density of red clump stars. And you see that starting from latitude -5, more or less here, you don't see a bar, you don't see an ellipsoid as you would expect, you see 2 blobs. And if you go down in the plane, you see that these 2 blobs get farther away from each other. While if you go up, more or less at the latitude of the window, -4, the 2 merge, and then you really see a bar. That's why everybody saw only a bar, because they were trying to stay as close as possible to the plane. While if you construct a vertical section passing through the minor axis, you see really the X. A much, much better way of seeing this is with the movie that comes from the paper from Weg and Gerhard, in which you see the global structure of the bulge, which is a bar. Then the sun appears. You see it from the side, and the bar looks really like a boxy peanut. That's the sun. You run a plane through it, and you see that when you arrive up, you see two blobs. And then a bar, and then again two blobs. So that was obtained using the data release 1 of VVV, which had some holes, so they assumed symmetry, and they got rid of the holes. It's really beautifully showing how the X-shaped or the peanut-shaped bulge looks like. And just let me go back to that. These are the four arms, or how you want to call it, of the peanut or the X-shaped bulge. How did we end up with an X-shaped bulge in the Milky Way? If you ask to Inma, who is not here, any dynamist, they have a pretty easy, they say, way, or natural way to produce this structure, which is the following. This instability, driven, for instance, by spiral arm, drive stars into the center in elongated orbits, so basically form a bar. This bar is unstable in the sense that stars in this elongated orbit at some point start bending, buckling, doing this thing. So ending up in families of orbits, stable orbits, which are made in the shape of 8, but especially in the shape of banana and anti-banana, I love the word, orbits, that really makes that X that we see. So it's a natural dynamical process that happens to bars. And so we are now in a position with our own bulge to go and verify in details if that's what happens. How? By measuring orbits of the stars in that places, which is what we did together with PhD student Sergio Vázquez at PUC. We got there where we see two red clumps. You see the luminosity function really have two red clumps, which are stars in the front and in the back. Get spectra, so radial velocities and proper motions. So in the end, 3D velocity for those stars. We had a sample of 450 stars. And then derive the 3 space velocity U, V, W. And compare those with the models. In this case, these are the models of Victor de Batista. This is a model of a galaxy that was not thought to be the Milky Way. It's just a galaxy that, in its simulation, happens to end up with a boxy peanut bulge. And as you see, there is an impressive agreement in the distribution of the space velocity. So we think that it's correct. Stars that we see in our own bulge have orbits like the banana orbits in the simulation. So maybe that's how they end up in this shape. However, if this is the way the bulge formed, how come we have a metallicity gradient? How can a dynamical thing produce a metallicity gradient? If you ask Emma, she says that it can, if all this process of a formation of a bar and buckling, etc., happens in a disk which has a radial metallicity gradient already. So if you cook that, you end up with a bulge that looks like this in IMA simulation. Qualitatively, it's pretty similar to this, I think. Okay, and the last thing I want to talk about is the NISO large program that we are carrying on with flames, observing 31 fields in the galactic bulge located in these positions. We are getting spectra at resolution of 6,000 for more than 5,000 stars in the region of the calcium triplet for all these blue fields, and high-resolution spectra for 450 stars at the latitude of Bade's window, but sampling longitude now. These are all my happy co-eyes. We call this program the giraffe inner bulge survey because compared to previous survey, for instance, the Argos survey, we are sampling really the innermost region. You see that these are the Argos fields, and we go much closer to the plane and to the center. And so the acronym of that will be GIBS. We are not native speaker, and we learned afterwards that GIBS means castrated male cat. That's okay. Too bad. After all, we have calcium triplet spectra, cat. We like the idea. We kept the cat. So we have a few first results in a paper that has just been accepted in Astronomy and Astrophysics. We have the kinematics for all our fields. And this is the radial velocity for fields at different latitude, very close to the plane, -2, -4, -8, -6. Our points are the red ones. These are the Breva points that do not get as close to the plane as ours, but we find similar results. So we confirm cylindrical rotation. And we agree with the models by IMMA, this one in black, of a bulge having only cylindrical rotation, so without a spheroidal component with more chaotic orbits. And something we did is to fit the mean radial velocity and the mean velocity dispersion all over the area we have, well, using the points we have, which are those. If we fit that with the plane, with the surface, we are basically making an interpolation so that if some of you go and observe in a field that we don't have, knows what to expect. So first, it is just an interpolation we provide. And second, this map is what needs to be compared with the maps from Saron, from any integral field of external galaxy. This is the rotation pattern of our own bulge compared to, as we would see it from an integral field. And this is the sigma map, which also has a very interesting feature that I was hoping to get Imma to analyze it. Apparently, I failed in this. Because there is a sigma peak in the center, very pronounced. I want to call it the inner stone, because I think it's tracing a very strong concentration of mass in the center of our galaxy. Also, this needs to be studied in more details. We have our own calcium versus iron calibration. Nothing especially new. There are 1,000 of calcium to iron calibration, including the one by Ricardo. We don't find anything new, but it's better to have this calibration for our own stars, bulge K-giants, so that we are sure it works. And it's linear, and it's like an extrapolation to high metallicity of what you find with globular clusters. And so with that, we will obtain the metallicity map for the whole bulge. We have also 4 fields observed at high resolution at the latitude of Bade's window. We already have the metallicity distribution. This is at high resolution for those fields. And they agree qualitatively with what we had in the map. So these are all preliminary results. That's why I just mentioned them, because we need to analyze them in detail. And the very last slide, before the conclusion, is I want to mention about the alpha element ratio in the bulge, which is important in terms of star formation timescale. Red points are bulge stars. Blue points are thick disk stars. Black points are thin disk stars. So as you can see, bulge stars are alpha enhanced, so they have a relatively high alpha over iron ratio, indicating a fast star formation. So if the bulge came from dynamical instability of the disk, which is what apparently happened, this is not a secular process. It needs to be fast. And it is compatible, bulge stars are compatible with thick disk stars in the common metallicity range, meaning that maybe this instability happened to the thick disk. Maybe. Instead, bulge star and thick disk stars are chemically different. So it's out of question that they had a common origin. Also, the age is pretty different. Okay, so I think I'm out of time. So I put my conclusion. I think I convinced you that the galactic bulge is very complex, and there is a Boxy pinot structure, X-shaped structure, but that's not all of it. The most metal-poor stars trace a spheroid. There are several independent observations that point to the presence of more than one component. In particular, the shape and the kinematics of stars of different metallicity are different. There is a metallicity gradient in the outer bulge that in the inner bulge seems not to be present. And bulge stars are old and metal-rich with high alpha-over-iron ratio. So they formed back in time, around 10 gigayears ago, fast. And that's it. Thank you.
Thank you. Thank you very much. We have time for questions. Yep.
Just, did you measure other abundances than alpha? Or alpha is magnesium?
Alpha is magnesium, titanium, oxygen, and aluminum. And silicon, we have silicon. I think we didn't publish it yet. There is manganese. Beatrice Barbui measured that in a sample of stars. Goes in the same direction. We have some UV stars in which you can measure barium and europium. A student in Nice was doing that. He didn't ever, he left before getting to publishing the paper. But it can be done and needs to be finalized. And from this spectra at 20,000, you really cannot get much more than this.
Is there any difference between the different?
No,
alpha?
not really. No.
So they are all
They are
together.
similar. And something important is that there is no difference with the position.
Okay.
So while the mean metallicity moves, you populate different regions of this thing in the x-axis, but the alpha over iron is always the same. You don't distinguish one field from the other.
More questions? Okay, so let's thank the speaker again.